Slug, weekly_world_models week, 2026 The W26, June 22nd to 26th, target, ~500 words, ~2.5 minute video. Everyone knows LLMs hallucinate. But what about world models? World models are generative AI systems that simulate how the physical world evolves. They're the engine behind robot learning, autonomous driving, and video prediction, and this week, a flood of new papers reveals they have their own hallucination problem. The good news? It's predictable, preventable, and the solutions are radically different from what works in language models. A landmark paper from UC San Diego introduces MMBench 2, a 427-hour, 210-task dataset for visual world modeling, and trains a 350M parameter world model on it. The authors identify three distinct hallucination modes: perceptual, tokenizer failures on unfamiliar scenes; action marginalized, the model ignores its input action; and scene diverging, multi-step rollouts drift entirely off the dynamics manifold. Their central argument is counterintuitive: hallucination in world models isn't an architecture problem. It's a data coverage problem. Because world models are trained on offline datasets, they inevitably encounter state-action pairs they've never seen, and they hallucinate, producing visually fluent but dynamically wrong futures. The paper shows these hallucinations are detectable at runtime using lightweight coverage signals, and more importantly, the same signals can guide targeted data collection to fix blind spots. A pre-trained world model can adapt to entirely unseen environments with as few as 50 real trajectories. This hallucination paper is part of a much larger movement. This week alone saw over 70 papers on world models and physical simulation. Let me highlight three that stand out. PhysiFormer treats physics simulation as a diffusion process in 3D world coordinates, predicting mesh vertex trajectories directly rather than generating 2D video. It handles rigid and elastic materials, generalizes to unseen geometries, and substantially outperforms autoregressive baselines. World action models, WAMs, go beyond predicting actions to generating future visual observations. Researchers used this capability to build Recurrent Generative Replay, a system where a robot can daydream its past tasks by generating synthetic practice data, reducing catastrophic forgetting by up to 50% without storing a single real demonstration. And at the theoretical level, a new paper from Peking University establishes the first generalization theory for JEPA-Based World Models, proving that latent space prediction fundamentally beats pixel space prediction because it navigates a trade-off between approximation error and sample complexity. World models are how AI will interact with the physical world. A robot that can accurately simulate the consequences of its actions before moving is safer, more sample efficient, and more adaptable than one that can't. But as the UC San Diego paper makes devastatingly clear, silent hallucination during rollout translates into silently incorrect decisions during control. The convergence we're seeing, generative video models learning physics, world models feeding into policy learning, theoretical bridges between representation learning and planning regret, this isn't niche. It's the foundation for embodied AI. We're approaching a world where LLMs don't just generate text, they run visual thought experiments. A fascinating paper this week called Einstein World Models proposes exactly this: insert callable world model rollouts into the LLM reasoning trace, treating visual simulations the way we currently treat code execution or web search. The last year showed us what scaling reasoning can do. The coming year will show us what happens when AI can actually imagine the consequences of its actions. That's this week in Frontier AI. I'm your host, catch you next digest.